The joints between the Great Pyramid stones are as precise as any modern machine shop could produce. How did ancient builders, working with what we call primitive tools, achieve such flawless perfection? This video will give you a clear, step-by-step understanding of the real methods behind history's most impossible constructions. We will uncover how stones weighing more than 100 tons were quarried, moved, and fitted together with microscopic accuracy, and why some walls have survived earthquakes for thousands of years while modern concrete crumbles. By the end, you will see these monuments not as mystical anomalies, but as masterpieces of human ingenuity, revealing a forgotten blueprint of patience and skill. What does it truly take to build something meant to last forever? This phenomenon of precision stonework echoes across continents and centuries. It is a story told in granite and limestone, a global riddle written in stone. In the windswept plains of Salisbury, England, the colossal sarsen stones of Stonehenge were hauled from quarries over 20 miles away, then shaped and fitted with mortise and tenon joints, a woodworking technique executed on a monumental scale. Far across the Atlantic, high in the Peruvian Andes, the Inca builders of sites like Sacsayhuaman constructed fortress walls from stones so intricately carved that not a single blade of grass can slip between them, each block a unique, interlocking puzzle piece. On a remote Pacific island, the enigmatic Moai statues of Rapa Nui, some weighing over 80 tons, were somehow transported miles from the quarry and erected upon vast ceremonial platforms. And of course, in the Egyptian desert, the pyramids stand as the ultimate symbol of this ancient ambition. These cultures were separated by vast oceans and thousands of years, with no possible contact, yet they all arrived at the same breathtaking conclusion, that humanity could reshape the very bones of the earth with nothing but persistence, observation, and ingenuity. This recurring pattern is the foundation of our mystery. It tells us we are not looking for one lost secret, but for a fundamental blueprint of human innovation, a way of thinking and working that was discovered independently, time and again. To solve the puzzle of how they built these wonders, we must first walk in their footsteps, beginning at the very source, the moment a mountain was chosen to become a monument. The journey from mountain to monument began not with force, but with profound observation. Before a single tool touched the rock, the ancient builder was first a student of the earth. This deep, generational knowledge of material science is our first principle. These artisans understood stone as a living partner, with its own personality, its own grain, and its own hidden weaknesses that could become a builder's greatest strength. They did not see a solid, impenetrable block. They saw a material waiting to be guided. This was an empirical science, learned through centuries of trial and observation, passed from master to apprentice. It was the essential foundation that made everything else possible. For example, Egyptian architects did not simply quarry any limestone. They specifically sought out the fine-grained, creamy stone from the Tura quarries across the Nile for the pyramid's smooth outer casing. They knew this particular stone could take a polish like no other, reflecting the sun with a brilliant white gleam. Similarly, the Inca builders selecting granite for their fortress at Sacsayhuaman understood how that incredibly hard stone would fracture and could be pecked into shape with other, harder stones. This material mastery extended to the very tools they used. They knew which local sands contained quartz or corundum, minerals harder than the granite they were shaping, and used these natural abrasives mixed with water to slowly grind and polish surfaces to a mirror finish. They understood thermal shock, the principle of heating a stone surface with fire and then rapidly cooling it with water, causing the outer layer to crack and spall away, a controlled method for removing large amounts of material. This was not a brutal struggle against nature. It was a collaboration. They learned to work with the stone's properties, not against them. By reading the rock's natural bedding planes and fissures, they could insert wooden wedges, soak them with water, and let the swelling would do the work of splitting a 20-ton block free from the quarry face with astonishing precision. This intimate, first-hand knowledge transformed an impossible task into a series of manageable, logical steps. It meant the builder was always one step ahead, using the material's own nature to achieve the desired end. Without this foundational wisdom, the most sophisticated engineering plan would have faltered at the very first obstacle. So the story of these impossible structures begins not with a blueprint, but with a question. What can this stone do, and how can I help it get there? With the right stone chosen, the next challenge was one of pure mathematics. How do you translate a grand vision from the mind's eye into the unforgiving reality of the physical world? The answer lies in a silent language of lines, angles, and proportions, a second principle we can call the geometry of perfection. This was not abstract theory scribbled on parchment, but a living, applied science executed with tools of elegant simplicity. The foundational tools of this ancient architect were humble, yet profoundly effective. A knotted cord became a measuring tape of infinite length, its consistent knots allowing for the replication of precise distances. A simple sighting rod, 2 sticks aligned by eye, could establish a perfectly straight line across a vast desert plain. And perhaps most ingeniously, the water level, a length of hollow reed or a stone trough filled with water, provided an unerring reference for true horizontal, a gift from nature's own physics that no modern laser could surpass in fundamental accuracy. With these tools, they conquered the landscape. They could lay out a perfectly square foundation for a pyramid spanning acres, ensuring its corners met at exact right angles. This practical mastery of the 3-4-5 triangle, the Pythagorean theorem in action, was used routinely to guarantee square corners, centuries before the Greek philosopher was born. But their geometry looked beyond the earth. It reached for the stars. Monuments like the Great Pyramid of Giza are aligned to the cardinal directions with a precision that still astounds surveyors, its north-south axis deviating by only a fraction of a degree. This was achieved by tracking the circular path of a star around the celestial pole, a patient, nightly observation that yielded a true north-south line. This celestial anchoring transformed a building from a mere pile of stone into a cosmic clock, a permanent fixture in both the earthly and the heavenly realms. So this invisible geometric blueprint was the non-negotiable framework. Every stone, from the largest foundation block to the smallest casing piece, was destined for a specific location defined by this network of lines and angles. The stone might be rough from the quarry, but it carried within it the precise dimensions of its final form, waiting to be revealed. The geometric plan did not just guide construction, it guaranteed it. It meant that work could proceed on multiple fronts, with teams shaping stones miles apart, confident that every piece would fit perfectly when brought together, like a planetary puzzle assembling itself. This was the silent conductor orchestrating the symphony of labor, the reason why these structures feel not just massive, but mathematically inevitable. Granite does not simply give up its secrets. To extract a 70-ton block from the living heart of a mountain required a dialogue with the stone itself, a conversation conducted through fire, water, and wood. This was the enigma of quarrying, where immense force was not applied but invited. The process began with a line carefully scribed by a master mason who could read the rock's hidden grain. Along this line, teams would laboriously drill a series of holes using simple stone or copper tools and an abrasive slurry of sand and water. This was a slow, rhythmic task, a patient percussion that could last for days. Into these channels, they would insert dry wooden wedges, often made from a dense, fibrous wood that swells powerfully. Then came the transformative moment. They would soak the wedges with water, As the wood absorbed the moisture, it expanded with a silent, relentless pressure, a force of nature harnessed for a singular purpose. The mountain would speak with a sharp, clean crack, and a perfect block would separate from the bedrock, following the precise line laid out by the artisans. It was physics made simple, a lever of incredible power created from a bucket of water. But stone has many languages. For other types of rock, like limestone, they employed a technique of thermal shock. They would build a roaring fire directly against the quarry face, heating the stone surface to a high temperature. Then, just as the rock glowed with heat, they would douse it with cold water. The sudden, extreme contraction caused the outer layer to fracture and fall away in sheets. By repeating this process, they could work their way deeper into the formation, essentially persuading the stone to remove itself. What is truly remarkable here is the absence of what we might expect. There were no explosions, no chaotic hammering against an unyielding surface. These methods required immense patience and a profound understanding of fracture mechanics, but very little brute force. They worked with the material's inherent properties, using its own responses to achieve their goal. It was a form of stone whispering. The block, once liberated, was not a crude lump. It was already a thing of intention, its sides relatively straight and its future shape implied. This careful extraction was the first act of precision, ensuring the material arrived at the worksite with minimal wasted effort. The mountain had yielded its treasure not through conquest but through a clever invitation, and with that giant now resting on the earth, an even greater puzzle presented itself. How do you move a weight that defies the strength of 100 people? The true test of an ancient engineer's skill was not in the carving but in the journey. A 70-ton block of granite is a sleeping giant, and waking it requires a different kind of magic, one of friction, leverage, and synchronized human will. The principles of moving these titans were deceptively simple, yet their execution on such a scale remains a breathtaking feat of logistics. We know they used massive wooden sledges, greased with water or animal fat to reduce friction, pulled along prepared causeways of compacted earth and stone. They employed rollers, likely sturdy tree trunks, placed beneath the sledge to create a primitive but effective conveyor system. But to see these as mere tools is to miss the point. The real innovation was the system. Imagine the orchestration required to move an Egyptian obelisk, a single needle of stone weighing over 300 tons. After its meticulous quarrying, it was loaded onto a gigantic, purpose-built barge and floated down a specially dug canal that led directly to the temple site. Upon arrival, the barge was carefully ballasted to tilt, allowing the obelisk to slide onto a waiting mound of sand built beside its final resting place. Then, with agonizing patience, workers would slowly excavate the sand from in front of the monolith, lowering it inch by perfect inch into a vertical position. This was not a single act of strength, but a multi-stage ballet of hydraulics, gravity, and counterweight, planned with the precision of a military campaign. And that reveals the deeper layer of this mystery. The how of physics is one thing, but the who is another. The social organization behind these efforts was itself a monumental achievement. To coordinate hundreds of workers, to feed and house them, to maintain morale and discipline over months or years of backbreaking, repetitive labor, this required a societal blueprint as sophisticated as any geometric plan. It was a collective endeavor that transformed a community into a single, purpose-built machine. The synchronized chants, the rhythm of pulling teams, the overseers directing every subtle shift in weight, all turned an impossible physical task into a manageable, rhythmic procession. The path of the stone became a temporary, moving monument to human cooperation. So while we marvel at the sledges and the ropes, we should listen for the echoes of the voices that used them, the collective breath of a civilization that decided to move a mountain, one determined step at a time. The sleeping giant had finally arrived at the worksite, but its true transformation was just beginning. A rough-hewn block of granite or limestone is a far cry from the perfect, interlocking puzzle piece needed for a seamless wall. This next stage, the art of dressing and shaping, was where raw material met human intention in a symphony of patience. It was a process not of swift cutting, but of gradual persuasion, where months of meticulous labor could be invested in a single stone surface. The tools for this task were elegantly straightforward. For the initial shaping of incredibly hard stone like granite, workers used hammers made from an even harder rock, such as diorite. They would literally pound the surface, not with wild swings, but with a controlled, rhythmic pecking that slowly pulverized the high points of the stone into dust. Imagine the sound, a constant, rain-like percussion across the worksite, as teams reduced a jagged face to a relatively flat plane, one tiny fragment at a time. This was a physical conversation with the material, a dialogue of impact and response, but a flat plane is not a perfect plane. For the final, hair's-breadth precision, they turned to the magic of abrasion. They used the sand beneath their feet, but not just any sand. They sought out sands containing quartz or corundum, minerals significantly harder than the stone they were shaping. This special sand was mixed with water to create a gritty slurry. Then, using a flat stone or a piece of wood as a tool, a worker would rub this abrasive paste back and forth across the surface of the block. It was a motion as simple as sanding a piece of wood, but executed on a monumental scale. With every pass, millions of microscopic quartz particles acted like countless tiny chisels, shaving away infinitesimal layers. The process was glacially slow, but it was also perfectly controllable. A master mason could feel the surface becoming smoother under his hands, guiding the tool to correct the slightest imperfection. Through this relentless, gentle grinding, a rough surface could be brought to a finish so smooth it felt like glass, and joints could be shaped to fit together with that legendary, paper-thin precision. The time commitment is almost incomprehensible to our modern sensibilities. Dressing a single large block for a pyramid's casing or an Inca wall could take a small team many months. This was not a race, it was a ritual of craftsmanship where the value was measured not in speed, but in permanence. Each perfectly flat surface was a testament to a profound cultural priority, a collective agreement that some things were worth the slowest, most careful work imaginable. The stone was not being conquered, it was being honored, transformed through unwavering dedication into a form that would defy the centuries. And once two such perfectly dressed faces were ready, they faced their ultimate test, the moment of fitting, where the invisible blueprint in the architect's mind would become tangible, locked in stone. That final moment of fitting was a silent, breathless test of everything that had come before. The hallmark of this ancient mastery is the seamless joint, a meeting of stone so perfect it seems to defy the very idea of two separate pieces. In many of these walls, the fit is so precise that not even a razor blade can be slipped between them, and no mortar was used. This was not an accident. It was the result of a meticulous, almost meditative process known as drafting, a technique that turns brute stone into a precision instrument. The process began with a simple yet brilliant trick. Before a block was set into its final place, masons would carefully bevel or slope the edges of the face that would meet its neighbor. They left a raised, rounded boss of stone in the very center of that face. Think of it like a proud button on an otherwise flat surface. This boss served a critical purpose. When the block was carefully lowered onto the stone beneath it, only the high points of these bosses would make contact. The masons would then gently rock the block back and forth. Where the boss touched the stone below, it would leave a telltale mark, often revealed by a pigment or dust spread on the lower surface. That mark was a map. It showed the craftsman exactly where the stone was too high, preventing a perfect fit. They would then painstakingly grind down that specific high spot, using their abrasive sand slurry, and try the fit again. Rock, mark, grind, repeat. This iterative dance could go on for dozens of cycles for a single block, each trial removing only the tiniest amount of material until the entire face made complete, even contact. The boss, having done its job, would finally be ground down flush, leaving two surfaces that married together with astonishing intimacy. This method required incredible patience and a deep trust in the process, as the final, flawless joint was invisible until the very last stroke of the abrasive. But some cultures took this concept of the perfect fit to an even more astonishing level. High in the Andes, the Inca builders developed a style that seems to reject right angles altogether. Instead of using rectangular blocks, they shaped each stone into a unique, multifaceted form with numerous angles and curves. Each block was a one-of-a-kind puzzle piece, carved to fit only its specific neighbors. When assembled, these irregular blocks locked together in a three-dimensional jigsaw of incredible complexity. This was not just for show. This interlocking design created a structure with a brilliant secret, a built-in resilience. During an earthquake, a rigid wall of rectangular blocks might crack along straight mortar lines, but an Inca wall, with its zigzagging joints and interlocking teeth, could flex and sway. The stones would shift and settle, then lock back into place as the tremor passed, a dynamic system that has withstood centuries of seismic activity. This approach reveals a profound philosophical difference. It is not about forcing nature into a perfect geometric grid, but about creating a resilient unity from countless unique parts. One culture sought perfection in the flawless plane, another in the intelligent lock. Both arrived at the same breathtaking result, a wall that stands not through adhesive, but through agreement, a silent testament to the belief that true strength lies in perfect connection. The Great Pyramid of Giza is a monument to a single, breathtaking idea, perfection on a planetary scale. To walk its base is to traverse a platform over 13 acres in size, yet it is leveled to within less than an inch from corner to corner. Its four sides are aligned to the cardinal directions with an error of just a fraction of a degree, a feat of celestial surveying that rivals modern engineering. And the millions of limestone blocks that form its core, some weighing many tons, are fitted together with a consistency that speaks of a universal standard upheld across decades of construction. This was not magic, but a masterclass in applied precision, where every technique served the uncompromising vision of a flawless form. The fine finishing of the stones, especially the now lost white casing blocks, was achieved with simple, relentless tools. Copper chisels, though soft by our standards, were effective on limestone when used with an abrasive slurry of quartz, sand, and water. This mixture turned the copper edge into a cutting tool of incredible durability, allowing masons to trim and shape blocks with controlled, patient strokes. The final polish, giving the pyramid its legendary gleam, came from hours of grinding with ever finer sands, a process that transformed rough stone into a mirror for the sun. But shaping the blocks was only half the battle. Placing them with such exactitude required ingenious solutions. One compelling theory involves the use of a temporary lubricant. A thin slurry of wet gypsum or clay, brushed onto the mating surfaces of two stones, could have acted as a hydraulic cushion. As the upper block was lowered, this slippery paste would have allowed for minute adjustments, letting the massive weight settle into its absolute perfect position. Once the water evaporated or was squeezed out, the block would lock in place, held by friction and gravity alone, with the fine residue simply brushed away. This simple idea turns an impossible task of millimeter alignment into a manageable one. The foundation for all this precision, however, was laid before the first stone was ever set. How do you create a perfectly level building site across an area the size of multiple football fields? The ancient builders turned the landscape itself into a tool. They likely dug a grid of shallow trenches across the bedrock foundation and filled them with water from the Nile's annual flood. Using the immutable law that water seeks its own level, they could mark a consistent height on the trench walls at the water's surface. By cutting the bedrock down to these markers, they created a starting plane of absolute flatness, a gift from the river that made every subsequent measurement possible. From this flawless foundation rose a geometry so precise it continues to whisper its secrets across 46 centuries, a testament not to lost technology, but to a culture that believed a building could and should converse with the cosmos. While the pyramids sought perfection in the plain, another civilization found strength in the unique shape. High in the Peruvian Andes, the fortress of Sacsayhuaman presents a breathtaking counterpoint, a symphony in stone composed not of identical notes, but of distinct interlocking chords. Here, the walls are built from colossal blocks of limestone and diorite, some weighing well over 100 tons, each one a unique, multifaceted puzzle piece. They fit together along seams of astonishing complexity, a zigzagging network of angles and curves that locks the entire structure into a single, resilient mass. This is not the geometry of the straight line, but the geometry of the living rock, adapted and assembled with a different kind of brilliance. The technique is known as ashlar masonry, but that dry term fails to capture the artistry involved. It was a process of profound conversation between the mason and the material. A stone would be roughly shaped at the quarry, then transported to the wall site. There, the real work began. The masons did not have a pre-drawn template. Instead, they worked directly with the stones destined to be its neighbors. They would carefully measure the gap, the negative space where this new block would reside, and then begin the slow, patient work of carving the stone to match that exact, irregular cavity. This was a trial and error process of breathtaking commitment. They would carve a little, then try the fit. Where it touched, they would make a mark. They would carve down that high spot and try again. This cycle of measure, carve, and test could be repeated dozens, even hundreds of times for a single block. The goal was not a flat surface, but a surface that mirrored the contours of its neighbors with such intimacy that the contact was total. The final fitting was likely aided by a simple, clever technique. They may have spread a soft clay or pigment on the faces of the already set stones. When the new block was levered into place, the high points would press into the clay, creating a perfect map of where material needed to be removed. This iterative dance, this physical dialogue between stone and stone, resulted in joints so tight that, centuries later, not even a pin can be inserted. The absence of mortar was not a lack but a statement. The structure's strength came entirely from friction, gravity, and the brilliant, interlocking design. This design held a secret purpose, one written into the seismic heart of the Andes. A wall of straight, rectangular blocks is rigid. When an earthquake's waves hit, that wall wants to crack along its straight, weak lines. But the walls of Sacsayhuaman, with their complex, three-dimensional jigsaw joints, are flexible. During a tremor, the stones in these polygonal walls can shift and rock slightly, absorbing and dissipating the energy. Then, as the shaking stops, gravity settles them perfectly back into their custom-shaped sockets. The wall settles, but it does not collapse. It is a dynamic system, designed not to resist nature's power, but to dance with it. This reveals a philosophical depth to Inca engineering. They were not imposing an abstract, perfect grid upon the world. They were creating a resilient unity from countless unique parts, a community in stone where every member, no matter how irregular, was essential to the strength of the whole. The wall stands not in spite of the earthquake, but because of it, a testament to building with the land, not just upon it. The tools of the ancient mason were extensions of the mind, each one a focused answer to a specific question posed by the stone. To see a simple copper chisel as primitive is to misunderstand its purpose entirely. In the hands of a master, with its edge constantly refreshed by a slurry of abrasive quartz sand, that soft metal became a relentless, precise cutting tool, capable of slowly, surely persuading even granite to take a new shape. The toolkit was a study in elegant specialization. Stone hammers, crafted from a rock harder than the one being worked, delivered controlled impact for rough shaping. Wooden wedges swollen with water became titanic levers of silent force. The plumb bob, a weight on a string, gifted by gravity itself, provided an unwavering reference for the true vertical. And the frame, a simple wooden triangle, transformed human strength into a controlled lifting force through the principle of leverage. The true genius was never in the complexity of a single tool, but in the orchestration of the entire set and in the profound patience with which each was applied. Consider the process of cutting a granite block with a copper saw. The saw itself had no teeth capable of biting into that immensely hard stone. Instead, the craftsman would pour wet quartz sand, a material harder than the granite, into the cut. As he drew the copper blade back and forth, the abrasive sand particles embedded themselves in the soft metal, turning the entire edge into a continuous line of microscopic cutting teeth. Each stroke removed a whisper of stone dust. It was a process measured in millimeters per hour, a testament to a cultural timeline where a single task could span seasons. The limitation was never imagination, but simply the rate of work, and this is where the social blueprint of these civilizations revealed its power. What one person could not do quickly, 100 people, working in coordinated shifts across years, could accomplish permanently. The scale of labor was the engine that turned slow, meticulous technique into monumental reality. This patience was not a burden, but a philosophy. It meant that every action, every stroke of the saw or tap of the hammer was intentional. There was no room for hurried, wasteful error because time was the one resource they had in abundance. The tool did not define the builder's ambition. The builder's unwavering focus defined the tool. Water was the silent partner in every stage of this ancient craft, a versatile tool gifted by the environment itself. Its most fundamental role was in establishing truth, the unwavering reference of the horizontal plane. Before a single foundation stone was laid, builders would dig a network of shallow trenches across the entire construction site. They would then fill these channels with water, drawn from a nearby river or canal. Here, they employed a law of physics so reliable it needed no invention, only observation. Water always finds its own level. By marking a consistent height on the trench walls at the water's calm surface, they created a perfect datum line that could be replicated across acres of uneven ground. Workers would then cut the bedrock down to these markers, creating a starting platform of absolute flatness. This simple, brilliant technique, using still water as a giant natural spirit level, is why the bases of the greatest pyramids are leveled to within a fraction of an inch over distances that would challenge modern surveyors. It was a principle of such elegant perfection that it remains in use by builders and engineers to this very day. But water's work was just beginning. Once the site was prepared, water became the engine of transport. By digging canals that linked quarries to construction sites, often timed with seasonal floods, builders could float massive stones on barges. A 100-ton block of granite, immovable on land, becomes buoyant and manageable when cradled by water, turning a Herculean labor into a graceful journey. This was logistics on a grand scale, harnessing the river's own power to move the bones of mountains. At the worksite, water transformed again, this time into the agent of perfection. Mixed with specific hard sands, it created the abrasive slurry that was the key to final precision. This gritty paste was the ancient equivalent of fine grit sandpaper, but on a monumental scale. Rubbed patiently across a stone surface with a flat tool, the slurry of water and quartz did the meticulous work of 1,000,000 invisible chisels. It could grind down the high spots identified during the fitting process, polish a casing block to a reflective shine, or shape a complex curve with flawless smoothness. The water served a dual purpose, carrying away the ground stone dust as it cooled the friction, allowing for continuous, controlled work. Some researchers have even proposed a more dynamic use for this elemental force. Theories suggest that by channeling water through a narrow leather hose or a hollow reed, ancient masons could have created a directed jet of considerable pressure. When such a jet was aimed at a stone surface already scored with a groove and fed with abrasive sand, it could have acted as a precise cutting tool, effectively water jet cutting millennia before the modern invention. Whether used for gentle leveling, powerful transport, meticulous polishing, or potential cutting, water exemplifies the core philosophy of these builders. They did not seek to overpower nature with brute force. Instead, they became keen students of its principles, learning to harness the inherent properties of the world around them to achieve ends that still leave us in awe. The greatest tool was not made of copper or stone, but it flowed freely from the river, a testament to the power of observation turned into action. These walls and monuments were not just built upon the earth, they were built in conversation with the sky. This is where the physical mastery of stone meets the intellectual mastery of the cosmos. For many ancient cultures, a building was not truly complete unless it also functioned as a giant celestial clock, a calendar carved in stone. The precision required for this was twofold, demanding flawless craftsmanship in the masonry and generations of meticulous observation of the heavens. The structure itself became the final, permanent instrument in a long chain of astronomical study. Take the Great Pyramid's near-perfect alignment to the cardinal directions, particularly true north. This was not a lucky guess. Modern analysis suggests a method using the simultaneous observation of a single star. As any star rises and sets, it traces a circular path. But there is a moment, as it crosses the meridian, when it is at its highest point directly north or south. By tracking a chosen star over many nights, ancient surveyors could identify this meridian passage with incredible accuracy. They would then mark that north-south line on the ground using their simple sighting rods and cords, a line that could then be extended for miles with unwavering accuracy. This technique turns the entire landscape into an observatory and the pyramid's foundation into a permanent record of that celestial measurement. But the alignments go far deeper than simple orientation. At Stonehenge, the massive heel stone is positioned so that on the summer solstice, the rising sun appears to balance perfectly upon it when viewed from the center of the circle. At the Temple of Karnak in Egypt, the axis is aligned so that on the winter solstice, the rising sun shines directly down the long columned hall to illuminate the inner sanctuary. These are not random events. They represent a profound fusion of cosmology and engineering. The precision of the stonework guaranteed that the astronomical event would be framed perfectly, year after year, century after century. A doorway off by even a single degree would fail to capture the sun's ray on the intended day, rendering the entire symbolic act meaningless. This meant the builders were working to a celestial deadline, their structural accuracy verified by the sun itself. The purpose was both practical and profound. These alignments created a reliable, immutable calendar for agriculture and ritual, tying the rhythms of society directly to the cycles of nature. They transformed the monument from a static object into a dynamic participant in the cosmic order, a stone witness to the turning of the year. The precision, therefore, was not merely for strength or beauty, it was for meaning. It was the final, essential step in weaving human achievement into the very fabric of the universe. But what if the stone itself was not a given? A provocative idea whispers from the edges of mainstream archaeology, suggesting that for some of these ancient wonders, the starting material was not a block quarried from a mountain, but a liquid slurry mixed in a pit. This is the theory of geopolymerization, a concept that turns the entire subtractive process on its head. Instead of seeing a stone and asking how to carve it, This theory proposes that ancient builders saw a pile of rock and asked how to rebuild it. Imagine the local limestone, soft and crumbly when first extracted, being chemically broken down. Proponents suggest using plant ash or natron, a naturally occurring salt, to disaggregate the stone. This process would separate the limestone into its basic components, creating a wet, clay-like paste. This paste could then be poured into wooden formworks or molds, tamped down to remove air bubbles, and left to chemically re-harden. The result would not be a carved block but a cast one, a man-made stone with a perfect molded shape. This idea seems to explain certain baffling features. How else, some ask, could stones at sites like the Valley Temple at Giza possess such complex, rounded, almost organic shapes that would be incredibly difficult to achieve with hammer and chisel? How could some surfaces appear fused together, as if the stone had once been soft? The theory suggests these are not carved features, but the natural seams and textures left by the casting process, the ghost of a wooden mold imprinted in reconstituted rock. It is a controversial notion, hotly debated within academic circles. Critics point out the lack of direct archaeological evidence for large-scale casting pits or chemical workshops at these sites. They argue that the proven techniques of patient abrasion and pounding are sufficient to explain the observed precision. Yet, the geopolymer theory persists because it speaks to a deeper question. It challenges our fundamental assumption that ancient technology progressed in a straight, predictable line from simple to complex. What if, alongside their mastery of physical tools, these cultures also possessed a sophisticated, forgotten chemistry? The idea is not that they had magic, but that they had a different kind of practical wisdom, a knowledge of how to manipulate the very substance of their world on a molecular level. Whether one accepts the theory or not, its value lies in the disruption. It forces us to look at these smooth, seamless walls and ask not only how they were carved, but what if they were not carved at all? It expands the mystery beyond the workshop, into the realm of the alchemist's fire and the chemist's vial, reminding us that the blueprint for these monuments may have been written not only in geometry, but in the silent language of transformed matter. The idea of sound shaping stone lives in the space between myth and fringe science, a resonant echo from our oldest stories. Across cultures, legends speak of builders who could command rocks to move with a chant or a specific musical note, floating massive blocks into place as if they were weightless. Today, some researchers look at these persistent tales not as pure fantasy, but as a possible, distorted memory of a real acoustic principle. The theory suggests that if you can find the precise resonant frequency of a stone, the specific pitch at which it naturally vibrates, you could amplify that vibration with sound waves. At a high enough amplitude, the stone might begin to behave in unexpected ways. The intense, focused vibration could, in theory, reduce internal friction, making the massive block temporarily more malleable or easier to move across a surface, as if it were gliding on a cushion of energy. Some even speculate that with perfect control over standing waves of sound, one could create points of acoustic levitation, suspending an object in mid-air. It is a breathtaking concept, turning air itself into an invisible tool. Yet, this is where we must carefully separate compelling speculation from archaeological fact. While the acoustic properties of ancient sites like the chambers within the Great Pyramid or the resonant galleries of Mayan temples are well documented and were almost certainly used for ritual and ceremony, there is no physical evidence, no tool mark or workshop residue, that proves sound was used as a practical construction method. The stones themselves do not bear the signature of such a process. So why does this idea hold such power over our imagination? It speaks to a deep human longing. Faced with achievements that strain our understanding of patience and labor, we are sometimes drawn to narratives of a lost golden age, a time of advanced science now forgotten. The acoustic theory, and others like it, fulfill a desire to bridge the gap between the monumental scale of these works and the simple tools we see in the archaeological record. They offer a shortcut, a key that would make the impossible suddenly plausible, but in doing so, they can unintentionally diminish the true marvel. The real story is not about a lost technology that made hard work easy. It is about a culture that embraced the hard work itself, that invested generations of careful effort into a single, enduring goal. The mystery is not lessened by acknowledging the sheer scale of human endeavor, it is deepened. It asks us to reconsider our own relationship with time and purpose. What does it mean for a society to commit to a project that none of its starters would live to see finished? That question leads us away from speculative tools and into the heart of the human spirit that wielded them. The true monument was not just the finished pyramid or wall, but the living, breathing society that built it. While we marvel at the stone, the most sophisticated tool of all was invisible, a blueprint of human cooperation. The sheer scale of these projects reveals a social engine of breathtaking complexity, an organizational machine that made the physical engineering possible. This was not a chaotic mob of laborers. It was a highly structured society with specialized roles, each a crucial gear in a grand mechanism. There were the quarrymen who understood the language of bedrock. The transporters, masters of leverage and logistics who moved the sleeping giants. The masons, the artists of the abrasive slurry who could feel perfection forming beneath their hands. The engineers and surveyors, the keepers of the sacred geometry that ensured every block knew its destined place, and the overseers, the conductors who synchronized this symphony of effort over miles and years. Each role required specific, deep knowledge, passed down through apprenticeship, turning individual skill into a collective capability. This level of specialization implies something profound about these civilizations. It means they had developed advanced, shared systems of communication, mathematics, and project management long before the first foundation stone was laid. They needed a common language of measurement, a universally understood set of geometric principles, and a chain of command that could translate a pharaoh's or a king's vision into daily tasks for thousands. Think of the logistics alone. To feed, house, and provide for an army of workers, not for a week but for decades, was a feat of social engineering that rivals the construction itself. It required planning agricultural cycles, establishing supply routes for food and water, creating temporary cities with bakeries, infirmaries, and administrative quarters. At the Giza Plateau, archaeologists have uncovered the remains of such a workers' village, revealing evidence of a community that was organized, fed with bread and beer from centralized bakeries and breweries, and even received medical care. This was not slave labor as often depicted, but likely a rotating core of skilled workers fulfilling a national duty, a civic project that unified the society around a common, transcendent goal. The ability to coordinate hundreds or thousands of individuals, to maintain morale and discipline through seasons of repetitive, physically demanding work, speaks to a powerful shared belief. The project itself became the glue that held the society together, a tangible expression of cultural identity and divine purpose. The rhythm of construction synchronized the rhythm of daily life. This social engine transformed human energy into a renewable resource. While one person might tire, the system did not. As workers rotated, the project advanced, inch by patient inch, year by steady year. The ultimate innovation, then, was not a secret lever or a lost alloy. It was the human capacity for large-scale, long-term collaboration. The real blueprint was written not on papyrus, but in the social contract that bound a community to a vision far larger than any single lifetime. They built not only with stone, but with trust, organization, and a shared story that could move mountains. The flawless joint in a pyramid wall was a testament not to a lone inventor, but to a chain of knowledge stretching back centuries. This precision was a collective inheritance, passed hand to hand and generation to generation in the most intimate classroom imaginable, the work site itself. The master mason did not teach from a textbook. He taught through action, through the patient rhythm of a demonstration repeated 1,000 times. An apprentice, often beginning as a young teenager, would start with the most fundamental tasks, perhaps hauling sand or mixing the abrasive slurry. For years he would watch, his eyes learning to read the stone's grain, his ears tuning to the different sounds a hammer made on granite versus limestone. His education was a slow immersion, a total absorption of craft through every sense. Only after mastering the basics would he be trusted to make a mark, then a cut, then finally, to shape a surface that would meet another with that legendary precision. This process could take a decade or more, a significant portion of a human life dedicated solely to learning how to converse with stone. The knowledge was not merely technical, it was cultural. It was encoded in the stories told around the fire at the end of a long day, tales of legendary builders and past projects that embedded lessons within narrative. It lived in the rituals that began a new quarry face or celebrated the laying of a cornerstone, ceremonies that tied the physical work to a deeper spiritual and social purpose. The so-called secrets of the craft, the exact recipes for abrasive slurries or the nuanced techniques for finding a stone's fracture point, were closely guarded within guilds or family lineages. This was not mere secrecy for its own sake. It was a powerful system of quality control and cultural preservation. By restricting advanced knowledge to those who had proven their dedication and skill through years of humble service, the tradition ensured that only the most patient and capable hands would execute the most critical work. It guaranteed that the standards of perfection, once achieved, would not be diluted or forgotten. This slow, human-centric transmission stands in stark contrast to our modern world of instant digital access and automated precision. Today, we can download a blueprint in seconds and a machine can cut a block with microscopic accuracy. But that ancient system cultivated something beyond mere technical skill. It cultivated a profound, almost reverential relationship between the craftsman and his material, a depth of understanding that came from a lifetime of focused attention. The monument that resulted was therefore more than an assembly of stones. It was the physical library of a living tradition, each perfect joint a silent word in a language of craftsmanship spoken across the ages. These ancient walls stand as a silent challenge across time, daring us to test their methods with our own hands. In recent decades, a new kind of builder has arrived at the foot of these monuments, not with cranes and steel, but with copper chisels, wooden sledges, and a profound respect for the original blueprint. These modern experimenters, teams of archaeologists and engineers, have undertaken a radical quest to strip away centuries of assumption and see if the proposed ancient techniques actually work, not on paper, but in the blistering sun with real stone. One of the most comprehensive efforts was led by archaeologist Mark Lehner and stonemason Roger Hopkins in Egypt. Their project was not a small-scale demonstration, but a full-scale, hands-on attempt to quarry, dress, and move a multi-ton limestone block using only tools and methods available to the pyramid builders. The results were both humbling and illuminating. They successfully split a large block from a quarry face using nothing but wooden wedges and water, the wood swelling with a sharp crack to release the stone exactly as the theories suggested. They shaped it with stone pounders and copper chisels aided by abrasive sand, and they moved it on a wooden sledge pulled by a team of workers over a prepared causeway. They proved beyond any doubt that the physics works, the methods are sound, but they also revealed the true, staggering cost, measured not in currency, but in sheer human effort and time. What a small team of dedicated researchers accomplished in weeks or months, an ancient civilization accomplished millions of times over, through a vast, coordinated societal effort spanning generations. These experiments serve as a crucial grounding wire for the mystery. They pull us away from pure speculation and anchor the conversation in reproducible physical reality. They validate the core principles of leverage, abrasion, and hydrostatic pressure. Simultaneously, they often disprove more fanciful or overly complex modern theories, showing that the simplest, most elegant solution was usually the correct one. Watching a 20-ton block inch forward on a greased sledge, moved by the synchronized pull of 24 people, is to witness a powerful truth. The miracle was not in a single, magical tool. It was in the sustained application of known physics, the relentless multiplication of simple actions across a vast canvas of time and human will. These modern replicators become translators, converting the silent language of the stones back into a vocabulary of sweat, rhythm, and incremental triumph. Their work does not diminish the ancient achievement, it clarifies it. It shifts our awe from the question of how it could possibly be done to a deeper appreciation of why a culture would commit to doing it, and what it tells us about the power of a shared vision when united with patient, skillful hands. This perspective invites a subtle but profound shift in how we view the past. We must guard against a form of technological arrogance, the instinct to measure ancient achievement solely by the yardstick of our own modern efficiency. For these builders, speed was never the primary objective. Their goal was permanence, perfection, and a profound alignment with cosmic and cultural order. What we might hastily label as primitive or inefficient was, in its context, a masterpiece of adaptation. Every technique, from the water level to the copper chisel and abrasive sand, was perfectly optimized for the materials, energy, and social organization they had available. To assume they must have possessed some lost, advanced technology, like power tools or anti-gravity devices, is not just speculative, it can ironically diminish their true genius. It implies that their observable, demonstrable methods were insufficient, that their intellect needed a hidden crutch, but the reality is far more compelling. Their ingenuity shines brightest precisely because it was forged within known constraints. They looked at a mountain, a river, and a society of people, and they devised a plan to rearrange the world using nothing but leverage, patience, and collective will. This is a different kind of sophistication, one rooted in deep environmental literacy and long-term thinking. Our modern world is built on the principle of rapid consumption and replacement, but their philosophy was one of eternal foundation. When we dismiss their slow, meticulous processes as impossible without a secret, we miss the point of their entire endeavor. The true lesson is not about a forgotten machine, but about a forgotten mindset, a scale of patience and purpose that challenges our own values. It asks us to consider what we might build if our measure of success was not quarterly profit, but millennial endurance. That staggering investment of time and effort forces us to ask a deeper question, one of purpose. Why would a culture commit generations to such an unforgiving standard of accuracy? The answer lies not in engineering manuals, but in the very soul of these societies. For these builders, precision was never just a technical achievement. It was a profound spiritual and political statement, a visible manifestation of their deepest beliefs about the universe and their place within it. In many ancient worldviews, the cosmos itself was seen as a perfect, harmonious order, governed by divine laws of geometry and celestial motion. A human structure that mirrored that perfection, with flawless lines and seamless joints, was seen as participating in that sacred harmony. It was a way of bringing a piece of the divine, orderly heavens down to earth. A wall built with such exactitude was not merely strong, it was righteous. It pleased the gods by reflecting their own flawless creation. In Egypt, the pyramid's perfect shape and alignment were a direct conduit for the pharaoh's soul to ascend and join the eternal circuit of the sun god Ra. The precision guaranteed the ritual's efficacy, making the monument a machine for eternal life. Similarly, the Incas saw their perfectly fitted stonework as a way of honoring the Earth Mother, Pachamama. The stones, fitted together without mortar, were thought to be alive and able to shift and breathe during earthquakes, a dynamic representation of living in respectful balance with a powerful, living world. The seamless joint was a symbol of unity and stability, mirroring the ideal social order. Just as each unique stone locked perfectly with its neighbor to form an unshakable whole, each citizen had a designated place within a stable, interlocking society. This symbolism extended directly into the political realm. A ruler who could command the construction of such impossibly perfect monuments was demonstrating a power that seemed to transcend the human. It was the ultimate proof of legitimacy, a display of divine favor and organizational control so complete that it could alter the landscape itself. The message to both the populace and rival kingdoms was clear. The ruler's authority was as immutable and well-founded as these stone mountains they built. Therefore, the drive for that paper-thin precision was fueled by a powerful convergence of motives. It was a devotional act, a political tool, and a philosophical ideal all at once. The mason shaping a surface for months was not just preparing a block, he was meticulously assembling a prayer, a declaration of power, and a model of the universe, one patient stroke at a time. This understanding transforms the monuments from puzzles of how into revelations of why. They stand as permanent testaments to what a society values most, to what it believes is worth the labor of centuries. The quest for perfection was ultimately a quest for meaning, etched in stone for the ages. The final, flawless joint was born not from a single perfect strike, but from 1,000 patient corrections. This is the third principle, the quiet engine of ancient precision, iteration, and incremental refinement. Perfection on this scale was not a starting condition. It was a destination reached through relentless cycles of trial, error, and adjustment. Each stone was, in a sense, a living prototype. The masons understood that error was inevitable in a process involving human hands and natural materials, so they designed their entire workflow around its systematic elimination. This was an empirical science in its purest form, a continuous feedback loop of action, observation, and correction. After a block was roughly shaped at the quarry, it would be transported to the worksite for its final fitting. Here, the real refinement began. Using simple wooden or stone jigs and templates, craftsmen could repeatedly check a block's angles and dimensions against a master standard. A jig might be nothing more than a wooden frame in the shape of a right angle, but when placed against a corner, it instantly revealed any deviation. These simple tools acted as physical memory, ensuring that the knowledge of the correct form was not lost between workers or across the years of a project. The process for achieving a seamless fit, like the one described earlier with the central boss, was iteration in action: fit, mark, grind, fit, mark, grind. Each cycle removed only the tiniest high spot revealed by the pigment or dust. There was no rush to a final answer, only a gradual, deliberate convergence toward perfection. This methodology transformed the entire worksite into a learning machine. The lessons from fitting one difficult block informed the quarrying and rough shaping of the next. If a particular type of stone from a certain layer of the quarry tended to fracture in an unexpected way, that knowledge was incorporated. If a new abrasive slurry mixture proved more effective, it was adopted. The project itself accumulated wisdom as it grew. This iterative approach was a powerful form of ancient quality control. It decentralized perfection. Instead of relying on a single master surveyor to check every stone, each team of masons had the tools and the mandate to constantly check their own work against the universal standard. This allowed construction to proceed on many fronts simultaneously without the whole project drifting into misalignment. A team working on the north face could be confident their blocks would match the dimensions of those being prepared for the west face, because both were using the same iterative process guided by the same geometric templates. The true scale of this patience is almost beyond our modern comprehension. A single obelisk or a particularly complex cornerstone might undergo hundreds of these trial fittings over many months. The investment was not measured in hours but in seasons. This reflects a fundamental cultural relationship with time. In a society building for eternity, a year of refinement on a single stone was not a delay, it was a necessary and respectful step. The goal was not merely to complete the task, but to complete it in such a way that it would never need to be done again. The monument, therefore, stands not as a snapshot of a finished idea, but as a physical record of its own becoming, a frozen moment in a long, slow dance of continuous improvement. Every seamless wall is a library of countless small corrections, a testament to the profound truth that the path to the impossible is paved with patient, repeatable steps. That iterative dance of trial and error was guided by an invisible master, a universal language of numbers and ratios. This language was given physical form through one of history's most elegant and enduring tools, the royal cubit. This was not a vague approximation, but a precisely standardized unit of measurement, carved into rods of black granite and meticulously maintained by temple priests. The Egyptian royal cubit was divided into 7 palms, and each palm into 4 digits, creating a modular system of remarkable flexibility. The consistency of this unit across centuries of construction is what made the prefabrication of stone blocks possible. A team of masons at a quarry 20 miles up the Nile could shape a block to be exactly 5 cubits long, 1.5 cubits high, and 2 cubits wide, following a detailed plan. They could do this with absolute confidence that another team, working on the pyramid's rising course miles away, was preparing a space for that exact block. This shared mathematical language turned a chaotic construction site into a coordinated assembly of precision parts. We have tangible proof of this foresight. Archaeologists have discovered ostraca, fragments of pottery or limestone, covered in grid-like sketches and calculations. These are the ancient equivalent of an architect's scaled blueprints. They show detailed diagrams of pyramid corners, the angles of ascending passages, and the layout of interior chambers, all rendered using the cubit as their foundational scale. This proves that the grand vision was first worked out in miniature, every proportion calculated, every stone's theoretical position assigned, long before the first foundation trench was dug. The mathematical sophistication extended far beyond simple measurement. The proportions of the Great Pyramid itself encode the constant pi, the ratio of a circle's circumference to its diameter. The pyramid's perimeter, divided by twice its height, yields a figure remarkably close to pi. This was likely achieved not through abstract calculation, but through a clever choice of slope, perhaps by using a rolling wheel to measure a specific distance for every unit of rise. This reveals a geometry that is both practical and profound, a building that embodies a fundamental mathematical truth of our universe. This use of standardized, sacred measurement transformed construction from a mere physical act into a ritual of cosmic order. The cubit was more than a ruler, it was a conceptual bridge, ensuring that the harmony conceived in the mind of the architect and the priest was translated without loss into the immutable reality of stone. It meant that perfection was not left to chance, but was baked into the process from the very first line drawn in the sand. The mountain was not an obstacle to be removed, but a partner in the design. This philosophy of environmental integration represents a fourth principle, one that moves beyond tools and techniques into a profound relationship with place. Ancient engineers understood that the most stable foundation was not one they built, but one they found, a truth written into the very bedrock of their sites. They did not fight their environment, they conversed with it, reading the landscape as a blueprint filled with inherent advantages. This was engineering as a form of deep listening. A natural rock outcrop, already settled for millennia, became the unshakable plinth for a temple wall. A strategically placed mountain peak served as a permanent back site for celestial alignments, a fixture in the sky that required no construction. Rivers were not barriers but highways and natural levels, their annual floods providing both transport for materials and the water needed for leveling vast foundations. This symbiotic approach minimized the most exhausting work, transport, while maximizing the one thing they could not create, geological stability. The entire construction calendar was often woven into the rhythm of the land and the community. Major work might be scheduled for the dry season, when the ground was firm and the skies clear for surveying, or for the period after the harvest, when a large portion of the population was available for communal labor. This was not just practical, it was sustainable, ensuring the project supported, rather than crippled, the society's ability to feed itself. The ultimate expression of this philosophy can be found in the rose-red city of Petra. Here, the Nabatean builders performed a kind of architectural sculpture in reverse. Instead of quarrying blocks and assembling them elsewhere, they approached a solid sandstone cliff face and carved downward, hewing temples, tombs, and facades directly from the living rock. The mountain itself became both the quarry and the final structure. This method eliminated transport entirely and created buildings whose stability was absolute, as they were literally one with the mountain. The natural strata and colors of the stone were incorporated into the decorative schemes, turning geological history into art. This approach reveals a mindset that saw the environment not as a blank slate, but as a collaborator. A river bend could define a city's shape, a prevailing wind could dictate ventilation shafts, and the path of the sun could determine every window's placement. By turning geographical features into architectural assets, these builders achieved a harmony that still feels resonant today. Their monuments seem to grow from the earth rather than sit upon it, because in a very real sense they do. This deep integration asks us to reconsider where a blueprint truly begins, not on a drafting table, but in the quiet observation of a place's soul. The smooth surfaces of these walls tell only part of the story. For a more intimate clue, we must look into the stone itself, into perfectly round holes drilled with a precision that seems to defy their age. In the granite quarries of Egypt and within the andesite monuments of Peru, archaeologists have discovered cylindrical cores, the solid plugs left behind when a tube was drilled deep into the rock. These are not rough, pounded holes. They are clean, circular bores, and the marks spiraling down their sides reveal a silent, mechanical truth. The grooves are uniform, deep, and evenly spaced, indicating a drill that turned with consistent speed and was fed into the incredibly hard stone at a steady, surprisingly rapid rate. The immediate question is blunt. How do you achieve such a clean, rotary cut in granite using what we believe were simple copper tools? A soft copper tube could never bite into granite. But a copper tube turned by a bow or a lathe-like apparatus and fed with a slurry of wet quartz sand becomes something else entirely. The abrasive particles embed themselves in the soft metal edge, creating a continuous ring of countless microscopic cutting teeth. Each rotation of the drill tube grinds away a whisper of stone, the abrasive slurry constantly renewed to carry away the dust and keep the cutting action fresh. Experiments have shown this method works. You can, with patience, drill a clean hole in granite with a copper tube and sand. Yet, the ancient artifacts present a lingering puzzle of scale and efficiency. The feed rate implied by the drill marks on some of these cores is remarkably fast. Modern experiments replicating the technique often proceed much more slowly. This discrepancy whispers of a possible refinement, a lost nuance in the process. Perhaps they used a specific, highly effective abrasive, like emery, from a particular source. Maybe the drill was weighted or leveraged in a way that applied optimal, constant pressure. Or perhaps the rhythmic, coordinated labor of a team turning a large capstan or bow drill could achieve a smoother, more powerful rotation than a small-scale modern test can replicate. These boreholes, small enough to hold in your hand, are monumental in their implication. They are direct physical evidence of a rotary machining technique, a technology of turning and grinding that was not just conceptual, but highly refined and routinely practiced. They prove that the ancient artisan's toolkit included not just the hammer and the chisel, but the precision drill, a tool that speaks to a desire for perfection even in the unseen, internal spaces of their work. This is not about massive force, but about controlled, rotational friction harnessed to create perfect circles deep within the heart of stone. The true measure of their work is not in its immediate scale, but in its enduring silence. While empires have crumbled and languages have been forgotten, these walls of stone continue to stand, having weathered countless earthquakes, centuries of harsh climate, and the slow erosion of history itself. This was not a fortunate accident. It was the direct, intentional result of a design philosophy that viewed permanence as the only acceptable outcome. Every decision, from the microscopic precision of a joint to the monumental sweep of a pyramid slope, was an investment in eternity. The legendary tightness of the stone fittings served a brilliant structural purpose. By creating a near-continuous surface of contact, the weight of the entire building was distributed evenly across thousands of points, preventing any single stone from bearing a catastrophic load. More importantly, these incredibly tight joints were not rigid locks. They allowed for a minute, almost imperceptible flexibility. During an earthquake, the stones in a wall like those at Sacsayhuaman could shift and settle against one another, absorbing and dissipating the seismic energy. When the tremor passed, gravity would simply settle them back into their custom-shaped sockets. This dynamic resilience, born from precision, meant the structure could dance with the forces of nature rather than fight them, a principle modern engineers now strive to replicate. Longevity was engineered from the ground up, quite literally. Builders carefully selected foundation sites on stable bedrock, not merely soil. They integrated sophisticated drainage channels within and beneath their foundations to channel away groundwater and prevent erosion or frost heave from undermining the stone. Even the iconic shape of the Great Pyramid is an exercise in environmental endurance. Its smooth, sloping sides minimize wind resistance and allow sandstorms to blow over and around it, rather than accumulating and exerting lateral pressure. The outer casing stones, polished to a mirror finish, shed water efficiently and resisted the abrasive kiss of wind-blown sand far better than rough rock. This holistic view treated every element as part of a single, immortal system. The precision was never an end in itself. It was the essential language of a durability strategy. The builders were not just solving for the moment of completion. They were solving for 1,000 monsoons, 100 tremors, and the relentless passage of millennia. They built with the future as their constant client, and by that most demanding measure, their work stands as an overwhelming, silent success. The seamless walls and impossible alignments begin to make a new kind of sense. When we weave together every thread we have followed, the deep knowledge of stone, the celestial geometry, the simple but brilliant tools, the mastery of water, the vast social engine, and the patient dance of iteration, a coherent and profoundly human picture emerges from the shadows. This is the final, crucial synthesis. There was no single lost secret, no magic lever or forgotten power source that explains it all. Instead, the explanation is a symphony, a harmonious convergence of many well-understood principles, each amplifying the others, all applied with a level of skill, patience, and shared purpose that stretches our modern imagination. The quarrier's understanding of fracture mechanics made the transporter's task possible. The surveyor's perfect celestial line gave the mason his unerring template. The society's ability to organize thousands allowed the iterative refinement of a single block to continue for months. Water leveled the site, floated the stone, and then became the agent of its final polish. It was a closed, elegant system where every output became an input for the next stage. This synthesis does not diminish the wonder of these places. In fact, it does the opposite. It transfers the awe from the realm of speculative mystery to the tangible realm of human achievement. The real magic was not in a tool, but in the mind that conceived of using it in such a sustained, coordinated way. The real power was not in a secret, but in the collective will of a culture that decided a project spanning generations was not just possible, but essential. We are left not with a void where an answer should be, but with a profound appreciation for the depth of practical intelligence and resilient spirit our ancestors possessed. They looked at the world around them, the mountain, the river, the stars, and their own community, and they saw not limits but partners in a grand endeavor. They asked not what they lacked, but what they could achieve with what they had, given enough time and unwavering dedication. The monuments, therefore, are not puzzles begging for a hidden key. They are answers carved in stone to a question we are still learning to ask. What can humanity build when it truly commits to a vision beyond a single lifetime? The silent stones have delivered their final verdict. This breathtaking precision was not a gift from beyond the stars or the relic of a vanished, super-advanced race. It is, and has always been, a towering monument to human ingenuity. The true wonder lies not in what they lacked, but in what they possessed in abundance, a profound intelligence expressed through patient observation and collective effort. They looked at a mountain and saw a quarry, at a river and saw a level, at a society, and saw an engine capable of moving the world. They transformed simple physics into a sacred craft, proving that material limitations are no match for a determined mind and a unified purpose. These structures are libraries written in granite and limestone, their pages the seamless joints and celestial alignments. They tell a story of ancestors who thought in scales of generations, who valued permanence over speed, and who believed a perfect line was a conversation with the cosmos itself. Their legacy is not a puzzle of missing technology, but a clear blueprint of what we are capable of when vision is married to unwavering dedication. They built for eternity, and in doing so, they left us a message that has weathered time itself. As we face our own modern challenges, from environmental resilience to the very concept of lasting legacy, their greatest lesson echoes across the ages. Perfection is not forged in the complexity of the tool, but in the clarity of the vision and the steadfastness of the hand that holds it. They remind us that our most enduring monuments begin not with what we can take from the earth, but with what we can learn from it and what we are willing to build together. What other ancient mysteries whisper to you from the depths of time? Share your thoughts below and subscribe to journey deeper into the forgotten stories written in the world around us.